Today, we're gonna be solving the science poorly answered quiz, which is basically a bunch of questions from the CA that many students found a bit difficult, and they put them all in one quiz so it can help you in your finals. Okay? So now, let's see. Which property can help distinguish between 10 grams of salt and 10 grams of sugar? Now, guys, salt and sugar, they almost look identical to each other. Okay, so let me just draw, let's say. See, they would look somewhat like this. The identical part, not the color. Okay, but let's say, not to confuse you, that this here is the salt and this here is the sugar. Okay, now, how can we tell the difference? Solubility in water. This is the correct answer from the very beginning. Now, guys, why? It's because salt generally dissolves faster than sugar in water. Because, for example, here I have these two cups of water, let's say. Okay? We have A and B. A is for the salt and B is for the sugar. So let's see. Obviously, when you put the salt in, it might actually just dissolve directly. Okay, so the salt particles, after a while, they're gonna dissolve. Okay? Meanwhile, in the same time, the sugar particles, they're still trying to dissolve. They're still trying, while the salt here just finished. You know, it's faster in dissolving, right? So faster in dissolving. Okay? So, how can you tell the difference solubility in water? Because if we know that sugar, it's slower, right? So we can easily tell that the one that didn't dissolve yet is the sugar, and the one that already dissolved is the salt. Now let's see why the other options are wrong. The volume is how much space it takes up. So how much space? But basically, let's say if you had this one cup and another cup, you filled one with sugar and then you filled one with salt. And let's say you put the exact same amount. Can you tell? No, you can't tell. Color, what did we say here? They look identical. Here, they look identical. Here. So obviously the color is also wrong. So remove volume and remove color. Temperature, you can't really tell the difference between sugar and salt using the temperature. How are you gonna do it? You're gonna measure the temperature for salt and sugar? No, obviously it's not gonna make sense. The mass is how much matter. How much matter. Or in other words, you can just say how many kilograms or grams. So basically, let's say once again you have these two cups. One is filled with salt and one is filled with sugar, right? It's not like the it's not like the salt is gonna weigh like 200 grams and the sugar is gonna weigh 100. This is actually really unlikely. So it won't make sense to do it using the mass. So here's a big hint for you guys. When you see 10 grams of salt and 10 grams of sugar, solubility in water. Okay? So solubility in water. Now, two beakers below are filled with different pure substances that have a similar appearance. Which property can be used to distinguish between these two substances? Okay. I'm just gonna zoom out a bit. Okay. I'm gonna zoom it back in later. But for now, let's keep it like this. So, these two substances, they said that they look identical. So they look the same. So they look the same, right? So if they look the same, which one do we eliminate first? We're gonna eliminate color, because then you can't distinguish between them using the color if they clearly look the same. Next, temperature. Can you do it using temperature? Like, what if beaker A and B were placed in the same temperature, right? How can you tell the difference? You can't. And also, guys, mass and volume. Let me tell you something here that's important. You use intrinsic properties to distinguish two substances. Okay? Now, guys, what are intrinsic properties? Intrinsic properties, they basically depend on the material. So they depend on the material, right? Or in other words, you can say it doesn't depend on the amount. Oh, doesn't depend on amount of matter. Okay? So this is why we also eliminate volume and mass. Why? Because volume is how much space. How much space. And how much space depends also on how much matter you have. So is it intrinsic? No, it's extrinsic. So this is wrong also. Mass also, how much matter. But for intrinsic properties, we clearly wrote that it doesn't depend on the amount of matter. So if you guys are still confused, it's okay. Here's a trick for you guys to know. You only use intrinsic properties to distinguish two substances. Why? Intrinsic, it basically depends on the material, right? Here we're looking for the material, the substance in beaker A and beaker B. We're looking for what material it's made of, right? We're not looking for how much it has, because also, guys, if you notice here, they're filled up to the same point. So how will mass and volume help us? They won't. Okay? So you can just take this down as a note if you guys want. It's that you only use intrinsic properties to distinguish two substances. Now, guys, if you want examples for intrinsic properties, there's conductivity. Because if I say an iron bolt, like lets electricity, like lets the heat pass through it. So an iron bolt, right? It lets electricity through. Lets electricity through, right? Does it depend on how much iron you have? No, right? Because can I say that like a 10-gram iron bolt lets electricity through, but a 2-gram iron bolt won't? No. Why? Because iron is a material. This is why conductivity is intrinsic. Also, guys, density. This one might confuse some of you guys. Density is the mass per unit volume. And what does it depend on? If you guys remember from term 1, density depends on the material, right? If I said the density, I'm just going to say actually, the density of 1 liter of water is 1. Can I say that the density of 10 milliliters of water is also 1? Yes, you can. Why? Because density depends on the material. Here are 2 examples if you guys want. This is why mass and volume, we don't use them. So what is our best option? The boiling point. Now guys, why? Different substances have different boiling points, right? For example, like, let's say that this substance A, boils at, let's say, 250, right? Will all other substances boil at 250? No, right? And also, guys, boiling point, it's intrinsic. Why? Because if I say water boils at 100, 10 milliliters of water boil at 100, right? Also, 1 liter of water will also boil at 100 degrees. Does it depend on how much water you have? No, it depends on the material, right? So what can you do? Boiling point. Once again, here, so back. Once again, why not mass and volume? Mass and volume depends on how much you have, right? But here they clearly look like they're filled to the same point, so obviously they're not gonna help you. Color, wrong. Why? Because they have similar appearance. And why not temperature? Because it doesn't really make sense to measure the temperature to tell the difference. What if they're placed under the same circumstances, right? Now guys, here, homogeneous and heterogeneous are the 2 main categories of mixtures, okay? Because, let me explain why the other options are wrong. Solution, now guys, a solution is a homogeneous mixture. Homogeneous mixture, right? Colloids, they're heterogeneous. We're gonna discuss them more later. Heterogeneous. Here. And also here. It's fine. I'm just gonna. Oh my goodness. Here, basically, solutions and alloys, both of these are homogeneous. And what are homogeneous mixtures? Homogeneous mixtures. They are mixtures like you cannot see different parts, right? For example, you have a salt water solution, right? Can you see the salt? Can you see it? No, you can't. This is why a solution is homogeneous. And what's an alloy, guys? An alloy is a metal. It's a metal what? It's a metal solution. Right? So solution is homogeneous. Because guys, did you know that gold, okay, it's actually made of gold and silver? It's made of gold and silver mixed together. Or copper, I think. But gold and silver most of the time. Okay? So gold is a mixture of gold and silver. But did you see the silver? No, you didn't. This is why alloys are homogeneous. Now, Heterogeneous are a bit different. We have suspensions and colloids. We said that they are, I'm just going to write it up here actually. Heterogeneous. Heterogeneous. Okay? So what does it mean? You can see different parts. Right? Now guys, what's an example? Suspension. What is a suspension? Suspension, think about it as here. S, okay? It's when large particles settle to the bottom and they're called sediments. Sediments. Okay? So what is suspension? A suspension is when large particles, I'm going to write large particles, settle and they're called sediments. Okay? So for example, guys, if you have here, oh, there's barely any space left. It's fine, I'm going to do it here. If you have, let's say, water, right? And then you pour in some sand, let's say. The sand here, it's going to act as the large particle and eventually it's going to settle to the bottom of the water. So guys, what can you see here? Here you can see the water and here you can see the sand, right? So can you see the different parts? Yes, you can. This is why a suspension is a heterogeneous mixture. Now, colloids are the opposite of suspension. Colloids is when small particles, you know, right, the small particles, they do not settle, but then they do not dissolve also. Now, guys, what's an example? Fog. Fog. We have also smoke, milk, whipped cream. All of these are colloids. Why? If you wake up to a foggy day, you can see the fog. Oh my goodness, where do I write this? I'm just gonna remove it. Actually, no, it's fine. I'm gonna deal with it. Fog. On a foggy day, let's say here you have a sky. And then up you can see all the fog. Like it's blocking everything in the sky, let's say, right? But will you just wake up and find all the fog on the bottom? No, you won't, right? So fog, does it settle? No. But does it dissolve in the air? No. Now here, smoke is really similar. Here. Smoke, if you woke up, for example, and then you find your room here, let's say there was a fire somewhere, you would see smoke in the air, right? But is it dissolving in the air? No. Will you wake up one day and then you could just see the smoke here in the bottom? No, you won't. So does it settle? No. Does it dissolve? Also no. I'm just gonna use milk and whipped cream another time. Like here. Milk and whipped cream. Okay? Now the milk here, if you poured milk into a cup of water, guys, generally the milk is just gonna float on top of the water. This is why it's a colloid. Whipped cream also, if you have, let's say this is the water, and then you pour the whipped cream on top. Let's say here, this is the whipped cream. Will it settle? No. Will it dissolve? No. But you guys might say, when you mix it, it will dissolve. Yes, but when you leave it like that, it won't dissolve. Okay? We might discuss these a bit more in other questions. So homogeneous and heterogeneous are the two main categories of mixtures. Okay? So just know this. When you see homogeneous and heterogeneous, they are mixtures. The ball and stick models shown below represent molecules of different compounds. The black dots represent O, which is oxygen, and the gray dot represents H, which is hydrogen. Which model best represents H2O? Now guys, first, what's H2O? We know that H2O is water. Okay? But this is how you guys read a molecule, okay? So basically, each element, it's gonna have its own number. So H2, how many hydrogen atoms? 2 hydrogen atoms. And when there's nothing next to the letter, it just means 1. So basically, it's the same thing as saying H2O1. So 2 hydrogen, and 1 oxygen. So 1 oxygen. Okay, we're gonna keep this in our minds right now, and let's see. The black dots represent the oxygen and the gray dots represent hydrogen. So here, for the gray, it's hydrogen. And in H2O, how many hydrogen atoms did we have here? We had 2. So hydrogen atoms is 2 atoms of hydrogen. Right? Now, the black is for the oxygen. Oxygen. Here. And when we said that there's no number next to the element, what's the number? 1. So how many oxygen atoms are there? 1 atom. So let's see. The one that actually represents the structure is 1. Now, why? Here we have the black dot to be oxygen. How many oxygen should there be? 1. Is there here 1 oxygen? Yes. There is. We also said here, how many hydrogen is there? Hydrogen has 2. And which color represents hydrogen here? Gray. Are there 2 grays? Yes, there are. Hydrogen. By the way, guys, just don't get confused. Like, don't say that an atom like this, looks weird. Right? So don't say that this looks weird, okay? Because it follows what we want. Here, for example, here we have only 1 hydrogen. How many hydrogens are we supposed to have? 2. So this is wrong. Here we have 2 oxygen. But in H2O, 1, it's supposed to be only 1 oxygen. So this is also wrong. Here it's way too many. Like, where did the 4 hydrogen come from, right? We only want 2 hydrogen. So wrong. Also, this one, once again, we need 2 hydrogen. And here it has 3. So which one follows our conditions? Number 1. Why? Because H2O, there is 2 hydrogen and 1 oxygen. And which one follows that? This graph. Okay? Question 5 says, a compound. Okay, guys, now you need to know the following. You need to know here. You need to know atoms. What's an atom? You need to know elements. Actually, I'm not going to write it in a table way. I'm going to write it like this. Atoms, elements, compounds, and molecules. Here. So, and you also, guys, you need to know the full definition. Now, guys, what's an atom? An atom is the smallest particle in matter. I'm just going to write the smallest particle that has the properties of its element. Here. Okay? Now, what is an element? It's a substance that cannot be broken down. Here, broken down any further. I'm going to explain them all after. Now, compounds is a pure substance with two or more elements. Here. And what's a molecule? Here, a molecule is something with two or more atoms. So when you see 2 plus atoms, it's a molecule. Now, let's explain them one by one. Here, let's say an atom. An atom, all you need to know is that it's the smallest particle of matter that has the properties of its element. Let's say here you have a gold bar. Let's say this gold here. Okay? What do you expect from the gold atoms? Now, guys, I'm just going to use a different color. The gold atoms, they're going to have the same properties as gold. Right? Because it's literally what's making up the gold. Right? So, they're going to have the properties of it. This is all you need to know about atoms. Now, elements is a substance that cannot be broken down any further. Now, what does it mean to say that? Let's say here you have H2O. Can you break it down? Yes. Into what? Hydrogen. And oxygen. So obviously, you can break it down, right? But for example, if you just have, let's say, oxygen alone, can you break it down any further? No, you can't, because it's a pure element. Now, compounds, pay attention to this part. Pure substance with 2 or more elements. For example, here, once again, I'm going to use the water example, H2O. What can we break it down into? We can break it down into hydrogen, and also we can break it down into oxygen, right? Hydrogen and oxygen. How many elements do we have? Here it wants 2 or more elements. We have hydrogen and oxygen. How many elements is this? 2, right? So we can have 2 or more elements, okay? So is H2O a compound? Yes, it is. Now, a molecule has 2 or more atoms. Once again, I'm going to use H2O. Okay? For example, here, how many atoms of hydrogen do you have? You have 2. How many atoms of oxygen do you have? You have 1. So how many atoms do you have in total? 3. So is H2O an atom? Yes, it is. I mean a molecule, sorry. Is H2O a molecule? Yes, it is. Now guys, atoms and elements, they're easy, right? The actual harder part is gonna be the compound and the molecule. But how I would think of it, compound is made of 2 or more elements. So let's say I have sugar. Okay, let's say I have, this is sugar. Okay, how would I want to look at it? If I ask myself, is sugar a compound? A compound, we know it's made of 2 or more elements. So I ignore the numbers. How many elements do I have? I have 3. Carbon, hydrogen, and oxygen. So, do I have 2 or more elements? Yes, you do. You have 3, right? Now, if I want to think about a molecule, I ignore the elements. I do the exact opposite here. I ignore the elements and I just look at the numbers. Here you have 6 molecules plus 12 molecules plus 6 molecules, right? So how many molecules you have in total? You have 24 molecules. Is this 2 or more? Yes, 2 or more atoms in a molecule. Okay? So, is sugar a molecule? Yes, it is. So take a look at the meanings. Okay, so what is a compound? We said a compound has 2 or more elements. Let's see first which one has 2 or more elements. First, we're going to cross this one because one element is wrong. Here, the smallest particle that has a property of an element, what did we say that is? That is an atom. But is it a compound? No. A mixture is made up of 1 or 2 no. A compound isn't a mixture. Now guys, the last 2 options are going to keep you a bit confused, but don't worry. They both have 2 or more elements. 2 or more elements. But which one's correct? This one. Because a compound is a pure substance made of 2 or more elements. Okay? Guys, don't get this one confused. When you see compound directly, pure substance. Substance. Okay? This is the first thing you think of. The 2 or more elements, this is the easy part that you should know. But also a pure substance. What's a compound? It's a pure substance with 2 or more elements. These are just basic definitions you guys need to know, okay? What is the main component of a solution in which substances are dissolved? Now here we move on to solutions. First, what's a solution? What type of mixture is a solution? It's a homogeneous mixture. Homogeneous mixture. Okay? So, a solution is made up of what? A solute plus a solvent. Okay? Think about it like this. The solute is the small part. Small. Solvent is the big or the main part. Okay, so let's make it more clear for you guys. Solution, I'm going to write a solution, for example, is equal to sugar plus water. Now, what is the small part that dissolves? Here, the solute dissolves. So, what do you think is going to be the substance that dissolves? Do we say water dissolves in sugar or sugar dissolves in water? We say that sugar dissolves in water. So, what's the small part that dissolves? The sugar, which is the solute. And the water, if you have here a full cup of water and a small plate of sugar with some, which one is bigger to you guys? This full glass of water or these tiny sugar particles? The full glass of water. And what's the big or main part? The solvent. Now let me give you another example. Solution, this time we're gonna say it's equal to gases. Oh, here. Is made up of gases plus nitrogen. Now guys, why is nitrogen here the solvent? Most of the atmosphere, what is it made of? Nitrogen. So this is why nitrogen is the big part. So big part. And what's the big part here? It is the solvent. So nitrogen here is the solvent. Now what is the small part that dissolves in the atmosphere? The other gases. Carbon dioxide, oxygen gas. Those all are the solutes. So gases are the solutes. This is why nitrogen is a solvent. Okay, they're gonna ask you this. So here are two examples you can take a look at. You can take these notes if you guys want to. And also this is important. If they ask you, what is the universal solvent? Think about it as what dissolves, like what helps almost everything dissolve? The water. Why? We could say water plus sugar, water plus salt, right? So many others also. So here, let's see. What is the main component? We said the main component, the big part, right? And the big part is the solvent, okay? Now here, what's the solute? The solute is the small part that dissolves, okay? But what's the big part? The main part, the solvent. Now right here, we're back to separation techniques. Which separation technique is shown below? Let's see what it's made of. Here, what's this? This is a condenser. Condenser. What is this? Receiving flask. But what is going to give us the biggest hint? This part. Because what's this part called? The distillation. Focus on this word. The distillation flask. So here, what's this word? Distillation. So what separation technique are we using here? Distillation or simple distillation. So this one, okay? So distillation. Here, this is really easy. Which separation technique is represented? Guys, in these few questions, they're just gonna be showing you a diagram probably and asking you the separation technique, okay? So go to the book and you can take a look at the diagrams. Let's see here. This thing here is called the funnel. Funnel. Okay, this here is a stand. This part isn't that important, just like this. This is a stand. And this here is the stirring rod. You don't have to memorize like the stand and the stirring rod, okay? I'm just doing this here. Stirring rod. Okay? You use a funnel when you want to filtrate something. So you use this to filtrate something, right? And if you want to filtrate something, what are you gonna use to filtrate something? You're gonna be using filtration. And also, if you want a bigger hint, this here, let's say that this is the water. This is some water that was went down. Let's say this here is sand in water. Sand in water. Right? The water that poured down, we call it the filtrate. Also, filtrate something. You use the funnel to filtrate something. And what's the water called here? The filtrate. And what do these two words remind you of? Filtration. So what separation technique is this? Filtration. Okay? Let's see, what separation technique is represented in the illustration below? See guys how they keep asking you the same thing? It's fine, we're gonna get through it either way. What's the biggest hint they're gonna give you guys? What is this? These two are papers. These two are the papers. And this substance down there is called ethanol. Okay? But here we already gave you the biggest hint we can. Here we have papers. So what do you expect to use when you have two papers? You're going to be using paper chromatography. This one, okay? Basically, what do you do in paper chromatography? You separate things based on what? Based on the structures of their molecules. Okay? But here you have the paper, and here you also have a paper. So, what are you going to be using, obviously? Paper chromatography. Okay? Let's go. Which of the following is an example of a chemical change? Now, guys, what's a chemical change? It's a change when new substances form. Okay? So let's see. Examples of chemical changes would be burning, baking, cooking, right? So let's see here. Burning sugar. What is it burning? Is a chemical change. Right? So this is correct. Oh guys, also rusting. Rusting. How could I forget? Why? Because rusting iron, it's gonna form a new material, which is what? Rust. So is rusting a chemical change? It is a chemical change. Okay? So correct. Cooking, it is also a chemical change. So correct. Now guys, why isn't freezing water not a chemical change? I am sure we said it before. Okay? A change in state, like freezing, melting, condensation, those are all physical changes. So physical change, right? Because let's say you have water, it boils, what will it be? Water vapor. You don't say carbon vapor, for example. Water turns into water vapor. right? It's still water, but in a different state. So is it a chemical change? No. Baking, what did we say is an example of a chemical change? Baking also, right? So is it a chemical change? Yes. So burning sugar, rusting iron, cooking eggs, and baking bread. See, here I want to select this, it won't. So 4 options only. What are 3 characteristics of gases? Now here, gases, their characteristics. Let us actually go through them one by one instead. They occupy the space they are in, correct? Why? If you have a room, let's say this is a room, right? The gas particles, they're gonna all spread across the room, right? Well, then if you put them in a small box, they're also gonna spread across the small box. So do they occupy the space they are in? They do. So these are here gases. So gas particles. Next, they can change shape but have a fixed volume. This is for a liquid. Why? Let's see here you have a glass of water, 100 milliliters. And then you pour it into a bowl. It's gonna take the shape of the bowl, but it's still gonna be 100 milliliters, even if it looks like it's more, right? But it's still 100 milliliters. Okay? So this is for a liquid. Is it for a gas? No, it isn't. Next, they can be expanded into larger volumes. Remember here when I showed you this room? This room clearly looks larger. Large. So here the gas expands. But here, look how small it is. So what do you think is going to happen to the gas? The gas will compress. Right here, compress. Okay, so let's see. Small, large. They can be expanded into larger volumes. Yes, they can. The particles, can they slide past one another? Guys, when you see slide past one another, this is for a liquid, okay? Because guys, liquid particles, they have the freedom to move. Let's say here, those are the liquid particles. They have the freedom to move. So they're going to be sliding to each other, bumping into each other. So when you see slide, it's a liquid. Is it a gas? No, it isn't. Gases are highly compressible. What did I write here? When it's a small space, the gas particles compress. Okay? So basically, they occupy the space, right? Whether it's a big or small space. They can be expanded into larger volumes, such as a small room, and they are highly compressible, right? If you put pressure on them, they're still gonna occupy that space. When you see they can change shape but have a fixed volume, this is liquid, and their particles slide, this is also a liquid. Okay? But here they want gases. What is one way to decrease the solubility of a solid solute in a solution? Okay. Here. This is something you need to know. Solubility and temperature. I'm going to write temp. But this means temperature, okay? Solubility. Ability here. And temperature. They move in the exact same way. If you wanted to have a higher solubility, you should have a higher temperature. If you want to have a lower solubility, you need to have a lower temperature. Okay? So let's see here. To decrease the solubility. So let's see here, to decrease it. Do you increase the temperature? No. Why? Because to increase the temperature, you need to increase the solubility. So this is wrong. By decreasing the temperature? Correct. Why? Because here, to decrease the solubility, you have to decrease the temperature. Correct. Let's see here why the other options are wrong. Here, by removing some of the solvent. Now guys, you can do that, but like it's not like when they're dissolved, you're just gonna remove the water, because you're gonna remove the sugar or salt with it, whatever dissolved in it. Maybe before you dissolve something, maybe you can remove. But here it just doesn't make sense to say, oh yeah, I'm just gonna remove some of the solvent, because the thing already dissolved. So it's too late for that. So no, wrong. By removing some solute from the solution, how are you gonna remove the solute? No, don't let these weird options confuse you. No, just no. We're changing the chemical properties, right? It doesn't make sense. So here once again, to decrease the solubility, you decrease the temperature. To increase the solubility, you increase the temperature. Okay? So to decrease the solubility, you need to decrease the temperature. Let's move on. A solution is a liquid mixture in which one of its components is uniformly distributed. Okay. Now guys, here, when you see the word uniformly distributed, uniformly means equally. So here it's equally distributed. Okay? Actually, I'm sorry, let me zoom out. It's gonna be way easier. So here, when you see uniformly distributed, they just mean equally distributed. Equally distributed. Okay? So now let's see. A solution. Okay? So what category of mixture does a solution fall into? Now guys, here you have two obvious hints. One, equally distributed, and two, a solution. What did we say a solution is? Can you see the different parts of a solution? No. So what type of mixture is it? It's a homogeneous mixture. Okay? Why? What two hints did they give us? It's equally distributed and it's a solution. So this is how we know it's a homogeneous mixture. What are the components of a solution? Remember when I wrote a few questions ago, is that a solution is equal to a solute. The solute is the small part that dissolves here, plus the solvent. And what's the solvent? The main or big part. So basically here, what are the components of a solution? What's a solution made of? It's made up of a solute and a solvent. So here, solute plus solvent. Now here it says underline the universal solvent. You guys remember I already explained it, but it's fine. Here, the universal, oh boy, universal solvent, yani the one that we that like dissolves almost everything, is water. Because for example, like when we're in science class, they say, oh yeah, imagine you dissolve sugar in water. Oh yeah, imagine you dissolve salt in water. What do we normally use here? We normally use water. So what is the universal solvent? The universal solvent is water. So let's just answer the questions. A solution is a mixture in which one of the components is equally distributed, uniformly distributed. That is a homogeneous mixture. Solution equal to solute and solvent. Solutes and solvents. And the universal solvent is water. Question 14. The law of conservation of mass states. So guys, here we move on to this one, the law of conservation of mass. This is what I need you to know. Mass always, absolutely always, stays the same. Stays the same. Right? For example, I have a piece of paper and then I cut it into 5 pieces. 1, 2, let's say 3, 4, 5. Let's say that the mass of this paper was 5 grams. So what do you expect the mass to be for all of these little papers? Also 5 grams. Did you make mass? No. Did you destroy mass? Did you remove it? No. So mass do not create, the law of conservation mass states that changes to matter, any physical or chemical change. Physical or chemical change do not create nor destroy mass. Let me give you an example for a chemical change. When you have a piece of paper and then you burn it, burning. Let's say ashes, the ashes that form around the paper, and the little crumbles of paper. Guys, ash, although it's a gas, gases are matter, so don't ignore their mass. And let's say the mass of the paper was 5 grams. The mass of the ashes and the crumbles and the remains of the paper will also be 5 grams. Did you remove mass? No. Did you add more mass? No. So in other words, mass is neither created nor destroyed. Okay? So changes to matter do not create nor destroy the mass. Let's see. The boiling point of 1 milliliter of water is 100 degrees. The boiling point of 10 milliliters of water is... Now guys, remember when I said intrinsic properties? Intrinsic properties. They depend on the material. And remember when I gave you this example? 10 milliliters of water boils at 100 degrees Celsius. So 10 liters of water, will it boil at 200? No, it's still gonna boil at 100. Why? Because the boiling point depends on the material, which in this case is water. Here. So, the boiling point of 1 milliliter of water is 100. So 10 milliliters of water, nothing will change. It will still be 100. Why? Because boiling point is an intrinsic property which depends on the material, which is what this case, water. So here, what kind of property is the boiling point? Let me just put the answer here. 100 degrees. So boiling point. Here we're gonna be, okay, here I'm gonna do this. We have a difference. We have here we have extrinsic. I'm gonna do this now actually. so that it doesn't confuse you. And intrinsic. They're different from physical. They're different from physical and chemical. Physical, chemical. Why? Extrinsic, I'm going to try to shorten it. Extrinsic, depends on the amount. Oh my goodness. Here it depends on the amount of matter. Intrinsic depends on the material. Material. Okay, now physical here, no new substances form. So you can observe without changing oh, so changing the identity of the substance. So what substance, oh boy, is made of? Okay, now chemical, you observe it also, but you change what the substance is made of. Okay, so now let's see what we can do. Non-intrinsic physical property, guys. Non-intrinsic just means extrinsic. But what did we say? The boiling point depends on the material. So is it extrinsic? No, it is intrinsic. So this is wrong. Let's see here. Intrinsic. Why? Because it depends on the material, so it's intrinsic. Physical property. When I say water boils at 100 degrees, will the water turn into carbon dioxide? No, right? So it's still water, just water vapor. So it is physical, right? I state to you guys, water boils at 100 degrees. Will the water change into carbon? No. Will it change into oxygen? No. It's still water that boils at 100 degrees. Why isn't it a chemical property here? If I say water boils at 100, once again, it won't change that it's water. So it's not chemical. So guys, boiling is intrinsic physical property. Why intrinsic? Because it depends on the material. And why physical? Because you observe it without changing what the substance is made of. Okay? So here, intrinsic physical property. Let's see here. An iron bolt is left to interact with water and oxygen. A reddish coating forms on the bolt. The red coating is called, okay, let me see here. What can be said, whatever, here. So let's answer. We said the iron is gonna form the red coating. Okay, how would I think about it? R for red, R for rust. So what's this red coating called? It's called rust. R for red, R for rust. Let's see. The ability of the iron to form this red coating is a chemical property. Why? Chemical, we said you observe it and then you change what it's made of. So you make an observation on this iron bolt. Okay? Now here it's made of iron. You're like, okay, I want to observe what happens when it rusts. So I take the iron bolt and I rust it. See here? It's not all red, it's brittle. Guys, brittle means it's easily like broken, okay? So now it's this weird rusty thing. So, did it change what it's made of? Yes, it did, because it turned from being steel, shiny iron to being brittle, reddish rust. So, it's a chemical property. Why? Because it changed what it's made of, the iron. What can be said about the identity of the mold after its interaction with water and oxygen? Now, guys, also, why is it a chemical property? It interacts. Interaction. When you see interaction, reaction, these are all chemical properties. So this is why it's chemical also. So what do you think happened to the identity? If it's a chemical change, it changed what it's made of. So obviously, what happened to the identity? It changes. Okay? So you could just take a look at it and let's put the answers. So the red coating, rust. The ability for the iron to form, it's a chemical property. Why? It interacted. So what do you think is going to happen to the identity? It changes. Why? Because it's a chemical property. Let's see here. When wood burns, it changes into gas and ash. Okay. So here, is the ability to burn a chemical or physical property? Let's see. When wood burns into gas and ash. Now, guys, the most important word here, it changes. And what did we say? When something changes, it's a chemical property, right? So is the ability to burn a chemical or a physical property? Chemical. Why? Because it changed into gas and ash, right? So why is it chemical once again? Because it changes. So it is a chemical property. Oh, just let me put the options here. So once again, before, when it changes, it is chemical. Also, CH for changes, CH for chemical. Also, if you guys want to know it that way. Let's see here. What best describes your answer in part A? We said that in chemical properties, it changes what it's what is it made of. Okay? So here, new materials are formed during burning. This is correct. Why? Because when something was burning, it formed gas and ash. So there were new materials. No new materials are formed. This is wrong because it's a chemical property, and in chemical it changes what it is made of. So this is wrong. The identity of wood doesn't change. Once again, it changes. Here, wood changes its state of matter? No way. Like the wood isn't going to turn into gas, guys, right? So let's see. Burning depends on the amount of wood? No, guys, here they're trying to trick you. Remember when I said what depends on the amount? Extrinsic. But here we're talking about chemical. So this is also wrong. Right? So please don't get mixed up. When something depends on the amount of matter, this is an extrinsic property. Remember when I discussed the extrinsic, intrinsic, physical, chemical? And I said the amount of matter of something is extrinsic, not chemical, extrinsic. So this is wrong. So why is it a chemical change? Because new materials were formed during the burning. So here, let's continue. The ability of a substance to burn. Oh, wait, sorry, just let me check something. We got it. Okay. Here, the ability of a substance to burn is classified as a chemical property. Guys, remember in the previous, like literally the previous question, it said the ability to burn is classified as chemical. Okay? Because when you're burning something, it could form ashes, gases, right? So when you burn something, ash, gases, right? And those are all new materials. When you burn paper, was ash already in the paper? No, it formed. So, burning makes new materials, and new materials are chemical properties, okay? So, here, chemical. See here. A 26-gram irregularly shaped pebble is placed inside a graduated cylinder filled initially with 24 centimeters cubed of water. The water level rises to 37 centimeters cubed after the pebble is added. Here, what is the volume of the pebble? Guys, here, to find the volume of something, we had a graduated cylinder. Let's say it was till here, and this is all 24 centimeters cubed. Now, you took the pebble. Here. And then you placed it in. What happened to the water level? It rose to, let's say up here. So now it's 37 centimeters cubed. When did it turn to 37 centimeters cubed? After the pebble was in. Okay? So what do we do to find the volume? We do 37 minus 24. You get 13 centimeters cubed. Now, guys, basically what I mean is, let me make it bigger and more clear up here. You have here two graduated cylinders. One when the object is in, one when it isn't in. Here, it was 24. Okay? And now, here, it's 37. 37 and 24. When? After you drop the pebble. Okay? So here, 24. This is 24. And now this is 37. You see? This thing, this amount of space that went up is the volume of object. Right? How much? So basically, how much it made the water rise is the volume. So how much did it make the water rise? 37 minus 24 is 13. So what's the volume of the pebble? 13 centimeters cubed. So basically just subtract. Okay? Why? Because the amount of like water that went up here, amount of water, of water, it's happening again here, water that went up is equal to the volume of pebble or any object. Okay? So it's equal to here. So here we just need to find how much it rose, and this is the volume of the object. Now we need the density, guys. So the density is equal to the mass over the volume. First, what's the volume of the pebble? We found it to be 13, right? Now we need the mass. Here, a 26-gram irregularly shaped pebble. It's in the question. So here, what's the mass of the pebble? 26 grams and 13 centimeters cubed. So now divide them. It's equal to 2 grams per centimeters cubed. Why? Because density is equal to the mass over the volume. The mass in the question here is 26 grams. And here we found the volume to be 13. And 26 over 13 is 2. So let's put the answers. 2.0, here 13, and here's the 2.0. Let's see here. How can the density of an irregularly shaped pebble be determined? Guys, remember in the previous question here, we had a graduated cylinder, right? Graduated cylinder, that's the name of the tool. Cylinder. Which is basically this thing here with labels, whatever you call it. Okay? Actually, let me make it more clear. Here. And here there are like labels. Okay? So let's see. How do you find the volume using water displacement? Water displacement. Now guys, what is water displacement? Remember when I said that here, for example, we have the graduate cylinder filled with 24 milliliters, and now it became 37, remember? And I said that the amount of liquid that went up is the same thing as the volume of the pebble. But here, instead of just saying the amount of liquid that went up, we will just say here the amount of displaced water. So guys, it's the exact same thing. So basically the amount of displaced water is the same thing as the amount of water that went up. Okay? So what method do you use? Water displacement. Why? Because the amount of liquid that went up, basically the amount of displaced liquid, is equal to the volume of object. So this here, all of this, is basically the liquid displacement method. Okay? How do you find the mass? Using a balance. Obviously, you're not going to use it using a ruler, right? Oh, wait, guys, before here, by the way, here I'm going to need to do this regularly shaped objects and irregularly shaped objects. Okay? For a regularly shaped double R. For a regularly shaped object, such as let's say let's just say here a cube, here a rectangular prism, a cube. For those, you take the length by the width by the height. How? Using a ruler. Okay? So for regularly shaped objects, you use a ruler, or for regularly, or for ruler. Now here for irregularly, we just use the graduated cylinder, which is basically water displacement. So using a graduated, I'm not going to rewrite it down here. Graduated cylinder. Okay, so you can take this as a note if you guys want. Okay, so here, how will you find the mass? You find the mass using a balance. Nothing else makes sense, honestly. So, how do you do the density? Density is equal to the mass over, which means divide, volume. So here, calculate the density by dividing the mass by the volume. Okay? So take a look here. So find the volume using water displacement, find the mass using a balance. And how do you find the density? By dividing the mass by the volume. Okay? So this is it for the first part, for the first half of the quiz. Okay? And we're gonna finish it up in part 2.